you very much for the organizer and all the sponsors and bother for putting this event. I'm honored to be among all the energy professionals. And right now I'm working in the venture capital world. We are swamped every day. People visit us. Most of them are hardware and software. So it's an honor for me. It's an honor for me to talking to the energy professionals. Before I start, so I want to do a quick survey. So how many of you are engineers? Show your hand. Wow. Management? Okay, yeah, that's about right. So how many investment? No. Okay, and then how many of you have heard the Amber Kinetics? Because quite a few of them, so I can run a little bit faster. So we had a CTO of our company actually come for CIE for last month or 2 months ago. So he did all the
in
November. So he did a full view of Amber Kinetics. So I'm only going to touch on a few things that I saw were interesting. Okay, so we got so how many of you are in the energy storage? Wow, great. Okay, so I love this field because I'm an energy background, and I think this, besides all the software, hardware, and all the programming, I think this industry is very exciting. It's new, and hopefully there will be more money coming into this industry, so we can grow this industry. And 5 years ago, I was a mentor for Clean Tech Open. And that time, there was someone told us, he said that the next unicorn is coming from Clean Tech. And 5 years later, we haven't found the unicorn yet, but hopefully in the next 5 years we find more. Okay, so I'm going to talk about the Amber from an investment perspective. Oh. Okay, now I'm out. Okay, so here's the topic, and okay, I'm a mechanical engineer, I can handle that. Okay, so you see the lower right corner is my QR code. So if you have your cell phone, gonna work?
It's too far away.
Yeah. Too far away. Okay, and the PPT, there's a big one. Come on. Okay, so we're going to talk about I'm going to run through very quickly the Amber Kinetics for people who has not heard of them. Then we go through the general investment logic, which I personally go through specifics, and then we talk about the technology. Since we have a lot of engineers in the house, that's good. Okay, Yangzhou already introduced, so we're going to jump through this. Okay, so talk about the mechanical flying wheel. We have a very old picture of a flying wheel. So the concept of flying wheel is always there. 5,000 years, 6,000 years. So I pulled a picture of an old one, and you can do transportation of water. You can do a lot of stuff with this thing. So specifically for the energy storage, what do you do with a mechanical device? So right now what we're looking at is we have a device, and we draw some vacuum. We put on a magnetic bearing, so it flows, and it does not reduces resistance. So what do we do with this thing? We take energy from the grid, and so we go through, well, the electrical system is very common because you got a motor, you drive the rotor, and you bring the speed up. So your energy is transformed from electrical to rotational energy, right? So now once you do that, at the desired moment, you can tell the device to release energy towards the grid or towards any appliances. So that's the basic concept. This it has been around for at least 100 years, and this is what we summarize the last 40 years the progress. And I want you to pay special attention to that red line, the time. That time is really the energy release duration, and it's a very important. It turns out to be a very important measure for storage. So in the early 90s, we have devices that use for electric cars, and the time is about seconds, similar to what the super capacitors does at this point. So in the next 10 years, we have it goes into a UPS, uninterruptible power supply, and the technology progress, so the time goes from seconds to minutes. So we have some commercial application in the 5,000 case in this type of technology. So the next decades, we have what we call the grid support. So you have at this time, the flying wheel has a few minutes of energy release time, and there is a grid support. You can hook up with the grid, you take energy, and then you can discharge back for various services provided to the grid. So now we're talking about coming back to the last 10 years. Now we're talking about large-scale grid storage. So the current measure is 4 hours. So at this point, the Amber Kinetic product, we all set the release time as 4 hours. It's very important because when you get down, if you go look at the any local utility, a time of day charging time, if you don't have an hour or about 1 hour storage time frame, you're not going to get on the grid network to provide any storage capability. So that's a brief rundown on the progress, and we go. Okay, so at this point, Amber they just finished off B round fundraising, and they have products in the market. And the first one is M32. 32 stands for 32 kilowatt hours. So it's not that big from grid, point of view. But their next products, which will be due to release next year, M160, so 160 kilowatt hours. Now that's significant because once you get into 100 of them put together, you're talking about quite a chunk of storage. And that's where utility companies start paying attention, because that could be used with a variety of applications that we're going to talk about. So we were talking about the high-speed rotor and the material. Now there was a specific technology associated with developing this technology, because when you have, early on they started all the rotor material, and when you pushing material, I think there might be a material expert here. When you go and push that material at a high rotational speed, you will find out that the speed actually causing the material, at a high speed, the material will actually, if it's not sturdy enough, they actually have what they call cracks when you're at a high rotational speed. So there's a special material science goes into it. And then there, of course, we want to shooting for high efficiency, so we have to reduce the air resistance and rotational resistance. So you have to put, and here's a mechanical engineer appreciate this. Think about very heavy. Think about a very heavy a rotor sits on a bearing because you have a rotational, right? So how do you support that thing and will not crush your bearing at a higher speed of rotation? Those are the issues that a mechanical engineer would appreciate. I'm sorry we got screwed up on the slide. So I put the breakthrough here, the first 4-hour discharge device, and the reliable minimum loss electrochemical system available at this point. Okay, so we just show a very schematic deployment of M160 at 32 megawatt. So you see it actually, because the high rotational speed, it has to be buried in a hole. So, and all you see on the ground is a top of the device, and then you have electrical panels with power in and power out. Okay, so since last couple of years, it has been widely reported with the progress of the Ember kinetics. So they've been reported by Wall Street Journal, Nature, PBS Nova did a special story for them, and CBS Sunday Morning. The last, I think this is last quarter. They are the winner of PD Magazine, A Re-Changing Technology First Prize. So this is the announcement. I'm sorry. This is the panel of judge for the magazine, and they won the first prize. So at this point, they have recognition in the marketplace. All right. So that's the introduction of the Ember kinetics. Next, we turn to the investment methodology. I have to claim that this is mine. It's not my venture capital. I follow this, but my partners follow other stuff. But we go in and then we have a very vivid discussion, and sometimes we don't talk to each other afterwards. Okay. So my experience in the VC world is varied, and I subscribe to four PCB. The reason is PCB is pretty cyclical. Everybody understand that, and it's very easy to remember. So, and I will explain what the 4 PCB is. So first, 4P. So what I'm looking for is problem, potential, product, and people. You have to solve a problem, right? And then we're going to talk about what problem that the Ember kinetics solve. Then we have to talk about potential, how big the market is. If you're looking at a niche problem, we probably say, great, you can make a living out of it, but we're probably not going to put money into it. And product is important. You have technology, but for different markets, you have to have product that meets the needs of the market, so people will buy it. And then, lastly, the people. Without the people, there's nothing. No, the above 3. So, okay. C stands for competitive advantage. We are looking for sustainable, and we can debate all day long what that means. We're looking for 3 years, 5 years. We will never know. Sometimes next year, somewhere, somebody invented a device that beats flying wheel. We don't know. Lastly, we're looking at the business model. Are you on the right track, or how are you going to sell your product? How are you going to make money? Okay, problem. We typically advise people to advise people to come with a very clear statement of problem they solve. And you have to think about, is that a real pain or itch point? We see a lot of people come in and they are talking about a problem, and we think, maybe I don't want to, maybe it's not a real problem, okay? So that's very important, because if you can, we run into a lot of issues with people that they are looking at it right. The underlying problem is real, but because they framing it in a wrong direction, they come out with the wrong product. It happens all the time, and that's why the startup fails 99% of the time. So there's many stories associated with this issue we can talk about. So let's look at the Amber Connecticut case. Okay, so as all the energy professionals know, and this has been going around for centuries, as long as we have electricity, we have this issue. When you have a network, because we don't have a large-scale energy storage, so the electrical demand, any instant, you have to have a supply. No, I'm sorry, it's the other way around. The demand has to match the supply has to match the demand. The other way around. Okay, so the problem with that statement is the supply keep changing. And that's our real issue. As you look at any California everyday energy supply, you see the changing all the time. We're going to have a supply curve to show you. So that's the real problem, and it's very old, and to the point that nobody remembers them as a real problem. So this is the first time in the history we actually have some technology, promising technology, that we can solve this problem, which means you have supply changing, and we can have a constant demand. I'm sorry. You have a demand that's changing, and you can have a constant supply, plus some storage to match that ever-changing demand. So that's a huge problem. The second one we try to solve is a lot of we call the microgrid. So you're talking about the island, you're talking about a data center, you're talking about a military base, industrial park. Those are the grid work. They actually don't want to use our state grid or the PG&E electricity, public utility electricity. They want to generate their own. So when you have your own network, how do you keep that steady? How do you still have the problem matching the supply with the demand? And this is the first time we also have some technology that they can use to satisfy that equation. The next problem, when we have if you think about this equation we just talked about, we have another wildcard coming in, not because the renewable energy. We all know renewable energy is intermittent, it's changing every day, and we don't know the day before what looks like the renewable energy supply looks like the next day. So we know that production in China for solar energy and wind energy, and we have see reports, they are losing 57 billion kWh in 2016. That's a lot of energy. What happened there is, let me show you. We can talk. I'm sorry, I didn't see it. So there was several issues associated with that problem. One is the grid people said, no, you're not getting on my network because you are intermittent, and we just can't take that much because the wind generates when the wind starts blowing, and solar is afternoon, or what happened at the evening. Nobody knows, right? So we have that problem. So the China network is the largest network in the world. They also have an issue because that's mainly a policy issue, because they cannot, once you get a network, because it's a balance issue. Some area has a very concentrated industry using a lot of energy. In the other area, unfortunately, in there, the solar and the wind all built out in the very remote area. So now you have a transportation issue. How do you transport energy from one area to the other? So that's the renewable energy issue. The fourth issue is we see a lot of electrochemical battery, and we have a lot of lithium is talked about. And they all have issue with cycles, performance degradation, which we call life. Some of them have fire, chemical release, explosion. Recycle is an issue, and then you got a pollution issue. So we try to make this world livable. And we have environmental pollution in manufacturing, operation, and disposal. After the battery is done, what are you going to do with that? So that's how we see the benefits of a mechanical device, such as a mechanical flying wheel can serve in this market. Okay, the second P is potential. How big is the opportunity? Well, I have to use story. I have asked this question to many of people come to my door and are asking for money. And they typically tell me huge. So I said, well, okay, in my good day, I will say how huge. In my bad day, I will kick you out, because huge is not a quantifiable thing. So we want you to, if you come to me and I want you to talk to our language. Our language is TAM, SAM, and SOM. So what is that? Let's look at it. So TAM is total available market. So you can estimate, you can go to a research paper, whatever they give you a total. There's a lot of data out there that you can pull from. As long as you tell me coming from a third party, we'll be okay. We're more interested in SAM, the serviceable available market. Now this is the key. This is the one that, this is, first of all, this is location based. So you can tell me worldwide is a serviceable market that you can serve with your product. We buy that story. But then we say, well, if you tell me why worldwide, then you are a startup company. You are registered, let's say, Silicon Valley. We may believe you can cover US. What about China? What about Southeast Asia? What about Europe? Can you cover that? Do you have money to cover that? So you're always limited by your resource. So the next thing we will ask you is, how much do you really think that you can attack the market? And with that SAM defined, and maybe you can take, the first year you can take 1%, and the second year you take 5%. I think it will be actually pretty good. So with that 1%, that will be your SOM, your serviceable, obtainable market. So if you can follow that methodology, which this is actually not mine, this is very common, we all use that terminology. When you go talk to a VC, that would be the language to use. Okay, so TAM. We're talking about the Amber Connecticut. So I just did I pulled a wiki for electrical energy consumption, top 10 worldwide. And I have that number and a PWH. I don't know what that unit is, so I looked up. It's called a PETA, and PETA is 10 to the 12th PWH. right here. 10 to the 12. A lot of electricity generated worldwide. And the reason I love this is because we said this is what? Nobody has solved this problem before, right? This is an entirely new market. Is that right? So we see people going to the existing market. Okay, existing market. So they have a problem because when their customer will say, well, yeah, I know this is the problem we have, but we already invested capital dollars into a device. It's still on the books, which means it's not a completely taken. They haven't ROI hasn't run out yet. They haven't run right off the so they cannot reinvest. We're talking about the wide open new markets that nobody has ever thought about before, and we're talking about what 10 to the 12th of kWh. Huge. Now I say huge. We can define that. Okay, so let's look at this is a general top summary for all the markets. We're talking about grid energy storage. We said based on the 10% of the power generated, we have 600 billion market. And the SAM is about 30 billion, which is worldwide. And if in North America, I would say 10 billion. That's pretty big market. The second market, the microgrid market, we're looking at 35 billion. And then the renewable energy market, we're looking at 350, I'm sorry, 2,000 billion, that's a lot. Okay, here's the California demand curve. This is, I think most of you are familiar with this. So before the renewable energy come along, this curve is in the afternoon. In the afternoon, this curve actually looks like this. This is actually this way, right? If you remember. And because the renewable energy, now in the afternoon, we're talking about a dip. And so most people call this duck curve. I call them Campbell curve, or whatever you call them. So we have a peak around the morning, and we have a peak in the evening. In the middle of the afternoon, it's a valley. Okay, so with that curve, we have generated another market, which we call the peak value energy arbitration. So a storage device can be charged at the afternoon and then discharged at the evening hours when you have the peak. And when you have that, if you go look at the PG&E's time of day charging, you will see we're paying 15 at the peak, I think, and we're paying, 8 or 9 at the valley. So that's we see a lot of, that's a growing market, and many people wanted to take the arbitrage market. And it's not a utility, anybody can do this. You just have to buy some equipment and put on the network, and you can generate. You can basically not generating, but you can make some money that way. Next, we have an industrial market. We're gonna run faster. Okay, we have telecommunication people wanted to have power supply, high speed rail people want energy storage, and many other people in the industrial market. We have charging station for the electric cars. A lot of work going on there. And we have a residential and a smart grid. We're going to jump over that. Okay, product. How different is your product that we're looking at from competition? That's where the product difference comes through. And how does your product market need, the product and market need fit, which we typically looking at, is there customer wants to pay for your product? And how much will they pay? This is the Amber Connecticut's customer shipments. So this is the firm contracts, they're shipping out to their customer. All right, the people, we're looking at their work experience, prior decision-making, prior entrepreneurial experience. The last one is very important, learning ability, because when you're in the startup world, many people give you advice. Who is right, who is wrong? Is the VC right? I don't know. Is the VC wrong? Maybe right. So how you can deal with that much input and figure out which is correct and take action, that's the key learning ability we're really, really focused on. It's not a degree. I think the Harvard startup failed as much as a state university, so degree is not an issue. Okay, here's the management team. I want to talk about Ed Chow is the CEO. Seth Saunders is the chief scientist. Seth is a professor from UC Berkeley. He has had this company for many, many years. He's an expert on the mechanical flying wheel. And he and Ed got together, start talking about this, and they said, we need to merge our company together so we can work together. That's how Amber Connecticut comes from. And I think Amber is the dog name of Ed. That's what I Okay, next letter is C, competitive advantage, sustainable. Well, let's look at it. Well, first, at this point, Amber is the only 4-hour discharge storage flying wheel system. The least amount of loss, we talk about that. And then we talk about the 3 to 8, 3 to 7 is the advantage over lithium battery. We're looking at no performance degradation. They can run 30 years with 20-year performance guarantee. No fire release, no pollution, recyclable. This things really I love because at the end of 20 years, you still have value in the device, and you can collect that, you can recycle that, and then you can reservice, and you can use basically like a used car. At 20 years, you can put a new life into a mechanical recyclable, device you can sell to somebody else at I don't know, 50%, 60%. And business model, we'll talk about this. Okay, so right now, at this stage, they are the integrated equipment supplier for grid, for whatever the different markets we just talked about. And then I think we want them to eventually become an energy and energy service provider. I think that would make the company more powerful. That's the next stage. And the other thing that this is especially in the North America, the SAS. We don't have a SAS for software anymore. We have SAS for energy storage. It's a new model that we see that 5 years down the road might be. We're paying, I think the PG&E is eventually going to pay for storage capability for whatever's on the system. Okay, how are we doing on the time? 5 minutes?
How many pages?
Oh, I can run through that time. Okay, so this is we can run this comparison with the flying wheel. The two biggest breakthrough is the 4 hours, and then the operation loss. The comparison with energy storage technology with lithium chemical storage. Those are the we already talked about. We did a lot of study regarding the lithium, sodium, flow battery, compressed air, the other technology that are under that. I think it's especially interesting. I want to show you some graphic interpretation. So this is a paper that we found. It was published in 2013, and they put their results very nicely in a graphic form. So I want to show you that. Okay, so this is the on the vertical is the discharge time, right? Yeah, discharge time. On the horizontal is the system power rating. So if you look at this chart, and it's actually for the section. So if you're in this region, you can only go after UPS and power quality type of markets. In here, you can go grid support, and in here, this is the storage, grid storage. So right now, in the grid storage space, only pumped hydro is solid storage, but that has an issue because the pump storage right now is 99% of the energy storage market is pumped hydro, which is what? So you have a hydraulic, so you have river and you generating hydropower. So what you do is at the bottom of the hydro, you pump that water back into the top and you store it. And that's what we currently have. And we can go look at the efficiency. So the other one is as far as the kilowatt hours goes, is the compressed air energy storage. And right now, Amber flying wheel, we can do 10 megawatt, 50 megawatt, we can do all of that. Okay, the next one. Next one, we're looking at the efficiency versus the lifetime. So if you go look at the efficiency in energy is very important, right? We're talking about if you have 1% in efficiency, we were talking especially the generation plant. 1% efficiency is a lot of kWh. So if you go look at it here, flying wheel is very high. We can, right now the Amber flying wheel, the published efficiency is at 88%. And we average can do 90%. So we're up there. And this is I think this is compressed air, this is the hydro. So hydro is about 80%, and compressed air is about 75%. So we're talking about 10% difference, or 15% difference. A lot of kWh compared with the different technology. I think the next one, we're looking at investment. We're looking at money. So this is the capital cost versus capital cost per kWh versus capital cost per unit power. So Amber right now is going from that direction. So this is M32, and this is M160. So this is really a nice curve we're looking at, right? Because we always say, in our world, we always say, no matter the technology doesn't matter because this is a lot of technology this is in the lab scale. You can go through that, you can do all kinds of things. End of the day, you have to be the least expensive technology to survive, or at least top 3 or at least 3. So I think that Amber really drive well in the cost down curve because we're going from very high to middle into here, and our end point is somewhere here, which we're talking about $100 per kWh, right? $100. This is really low. I think the lithium right now is at 250 to 300, and they can go down to maybe 200. If the flying wheel can go down to 100, that's a huge deal. And I think that they have potential because we're talking about their old steel. There's a lot of steel. 90 to 95% of the components is steel. So steel is cheap. China has a lot of it. This is my QR code. I think everybody's waiting for that. Questions?
So how about that? Have already
I ran
okay.
Okay, while they're setting that up, let me just say a couple of words to begin. Thank you very much for this opportunity to come and speak with you. about energy storage. This is an area that I've been working on for about 15 years now, a little bit longer than that. And a lot has changed, as you can imagine, in the last 15 years. We have seen a great deal of progress. I really liked Jason's presentation because I think it really addressed the investment perspective on storage very well. And of course, everybody, as he pointed out himself, everybody has a slightly different view on these things, and I also have a slightly different view based on my experience in the area. One thing is, as he pointed out, energy storage is the question is when you're looking at an investment in storage, is it a pain point or is it an itch point? And one of the interesting things about storage, I think, is that today, if we're perfectly honest, I believe it's an itch point. Because right now, the grid is working very well. And all of the problems that we face, that we're trying to address with storage, for example, renewables or curtailment of renewables, many of those things are not that big a deal. We're not going to have a serious issue because we're losing a little bit of solar energy. However, that's going to change in the very near future. And as we get increasingly reliant on renewable energy, as we're looking for an ability to deliver electricity at lower costs and more reliably all around the world, storage will become increasingly important. And there will come a day when you won't be able to live without it. So I think it's very wise to try to anticipate where the hockey puck's going rather than trying to see where it is right now. And that's a very important part of what we're looking at. In the electricity industry, we have a habit of looking at where it is right now. And many people look at it and say, well, that doesn't make sense. We don't need energy storage. And there's two things I always like to address that with. One is the smartphone. Everybody knows about the smartphone. It's only about 10 years old, right? So it's only been announced 10 years ago. When it first came out, nobody said, oh, you know what, that was a pain point. That was something that we needed right now. It wasn't. But today, if you took away all the smartphones, that's a pain point. Right? It's a pain point. How many people here have been able to go the whole time for the last 2 hours without taking out your smartphone? So, yeah. Yeah, there you go. So, that's the thing. The other thing is, sometimes people talk about these things in terms of cost, and they say, well, this doesn't make any sense in terms of cost. And the thing I always point out is another thing, bottled water. Bottled water makes absolutely no sense. You are paying $2, $3. Sometimes you go to the airport and you have $5 bottles. But I want to try to look at some of the details of that value proposition. So just to introduce ourselves, Jen mentioned already what we do at EPRI. We are an independent, nonprofit, collaborative research institute doing public interest research in energy and the environment. And what we are really trying to do is focus on those technologies that can make electricity safer, lower cost, more reliable, and more environmentally responsible. Because we believe that electricity, like energy in general, energy is a public good. The more we have, the better it is. And we want to be able to do that with minimum impacts on people. And the impacts include environmental impacts, but they also include cost, and they include reliability. So we have to make sure that we're available to try to address those things. And that's we're one of many agencies that do this, and we try to do this very collaboratively with all of the groups that are out there. We do a great deal of work, for example, with the California Energy Commission. Mike will be talking later, and we're very grateful for their support. But we also work with many universities. We may be working with many of you in this area. So I've got a pretty quick agenda to go through. I just want to go through a little bit of overview of what we're doing today in energy storage, talk about the benefits, talk about the costs, and how the accounting for costs happens, and then the path forward, which will involve all of you. And I hope that everybody will be, you're here today because you're interested in storage, and I hope that you're interested in being a part of the future. So let me start with the overview. The whole purpose for storage, as Jason said, is that we're addressing the need for being able to store electricity, which is not something that we did in the past. Historically, the grid has operated so that supply is equal to demand. So by introducing inventory in that system, we can change a lot of things. Historically, when we looked at the grid, when we looked at food supply, it was the same situation. You had to take the stuff immediately after you grew it, and then you had to eat it immediately. And so that limited your options. When they created refrigeration, that changed a lot of things. And remember that it's not simply a matter of inventing this. Refrigeration was invented more than 100 years ago, but then it became cheaper with time. And as it became cheaper, more and more things were available. So at some point, it became so cheap, refrigeration became so cheap that it's everywhere in the supply chain. Not just at the production point, not just at the end point. It's everywhere in that. And that changes everything. Changes delivery systems. You don't need the milkman anymore. He would come by every day and deliver milk. You can go and buy milk anywhere you want, and you can keep it as long as you want. And so it creates new supply and demand patterns. So we don't even know what will happen when we add energy storage to the grid. All we know is that it will be transformative. It's going to be a big deal. So those technologies, those companies that have technologies, like Jason pointed out, will make a big difference in how this all works. So the drivers for that are many. I don't want to try to imply that it's just a technology driver. The energy industry is recognized and has been recognized for a very long time as a key part of society, and so it's heavily regulated, very heavily regulated. And so government, the way that the government treats energy is going to impact the way that energy storage is implemented. Economic transformation, we've seen costs, of course, decline, but also seeing new business models, service providers, for example. Societal change with increased environmental awareness. And again, electricity has become more important than ever. You lose internet for an hour, people go crazy. What about the grid? The grid's even more basic need. And we just don't think about it. When you flip that switch, you expect the light to be on. And then technological advancement. You've seen the changes that have happened over the last few years to make new storage technologies available. And a lot of that has been influenced by these technologies in information. So the reason we have better batteries today is not because of the need for an EV, it's because of the need for a better cell phone, for a better laptop. And those are really what's driving the technology today. Although in the future, I think the impact will be even greater in the transportation and other sectors. So, of course, I usually try to talk about the hype curve. Many of you are already familiar with the Gartner hype curve. It was developed by Gartner in the 70s. Any new technology starts out with a trigger, and then immediately the visibility of that technology goes very high to that. And you reach a point where it's everywhere. You see it in the news, you see it, you can't avoid it. It becomes like, like some things today that are very popular, like kale. It seems to be in every last little thing. And then that's called a peak of inflated expectations. And then afterwards, people get tired of it. And they don't get tired of it because it's not working. They get tired of it because it's not delivering everything it's promised. And so there's this backlash, a little bit of a backlash, down into the trough of disillusionment. And then gradually you have to work your way up out of the trough of disillusionment into the plateau of productivity. You've seen these progressions, for example, with the internet. When first the internet was everywhere, then everybody said, oh, well, this can't be monetized. We're not going to make any money on this. And then we're into the trough. And then now, of course, once again, it's ubiquitous. It's everywhere. And everybody just takes it for granted, and that's where we're on the plateau of productivity. So storage is going through the same kind of things. Many of these technologies are, and I put them on this graph where I think they are. This is not a, obviously it's my opinion, and different people will have different opinions, but there's also no guarantee on how fast these things are going to move up out of these things. I actually think that, a few years ago I put energy storage at the top of that curve, the top of that peak of inflated expectations, because everybody was saying, if this was a few years ago, you may remember, 2011 was the year of energy storage. 2012 was the year of energy storage. 2013 was the year of energy storage. And then after that, they started saying, okay, well, maybe we shouldn't call it that anymore. And went down into the trough. And now it's coming back up, and it's gradually, people are looking at it, but they're a lot more cautious this time because they have gone through those effects. Now, all of the companies today are going through the valley of death, and they're trying to make it up this curve. And that's not an easy curve to come up, the second curve up here. You can't live off the hype on that one. So they're trying to get out, but they're going through that. And the thing is, like, behind-the-meter storage is very instructive. Behind-the-meter storage came after many of these. Remember the Powerwall in 2015? Powerwall was going to be everywhere, right? Everybody was going to have one. Everybody and their dog was going to have one. And in fact, I actually bought one for my dog. I didn't buy one, I just put the order in just to show that it can be done. You know, I mean, it's hype, but it's not real, right? I mean, it's not, you know, Tesla tried to get my dog to buy a different product because they knew that the Powerwall didn't necessarily make sense. And they were learning. And, you know, I'll talk about that a little later. They're a very, very effective company at transforming their business models. You know, they've done some good work in that area. But in the meantime, for behind-the-meter energy storage, you've seen the shine fade off of that. And so right now, there's tremendous progress being made, but it's all hidden. You don't see the big press releases because people are still learning. The progress moves on, even though the visibility right now is still falling. So gradually, the visibility will come back. And you're starting to see that again, and you're starting to see a little bit more hype. So the question is, you know, are we reaching the tipping point as far as some of these things? Because the cost has come down to the point where it's very attractive in a lot of different applications. It's still high. You've seen some of these numbers, and there's a lot of numbers that are thrown around out there. I'm not going to try to go into the detail here. If you're interested, come by and talk to me afterwards. But you know, some of these estimates that we're looking at are for lithium-ion are pretty low and already going below what we estimate for 2020. So the prices today in 2017 are already looking cheaper than 2020's estimates. So that's pretty impressive. That's a very fast reduction. And so what we're seeing is that the prices for lithium-ion, at least, are reaching a very interesting level. And that's opening the market. And I don't want to say that lithium-ion is the solution, by the way. There are lots of technologies that are going to be the solution. But what lithium-ion is it's opening the door. It's the first technology that's opening the door to energy storage. And then there are other technologies that will come along and are going to be important in the future. We shouldn't think that the problem is solved with lithium-ion, because it's certainly not. And Mike will be talking about that as well. So, but there are still gaps. We're seeing some interesting progress, but there are still gaps. And the big gaps, one is real-world performance data. We don't really have any. People talk about these systems that are getting installed, like the Tesla system in Australia, and they declare victory the moment it's installed. That's like declaring, you know, oh, this car is great the moment you drive it off the lot. You don't know it's a lemon until a few months in, right? So we want to see how these technologies perform. We want to see how these products perform and what the real value is and the real operation is. And historically, to be frank, they haven't worked very well. I put these two pictures up here because these come from companies that are no longer existing, who have produced products that didn't quite work out the way they wanted to. But you know, it's a cautionary tale. Let's not declare victory prematurely. But even more basic than that is understanding the value of the storage, knowing what it's for. Like I said, the value proposition is not immediately clear. And I compare this again to the smartphone. When the smartphone first came out, people said, I'm not going to pay $800 for that. And now we have smartphones that are going for more than $1,000. And then organizational adaptation, just being able to incorporate storage into the way we run the grid is very important. Today I'm going to focus on just that centerpiece, the understanding the value, and just that area of getting the most value. And so I want to talk about potential benefits of energy storage. And I'm not going to get too esoteric, but it's going to go a little bit into the markets and the way that things work. So what are the potential benefits? They come in several different classes when we're talking about how storage adds benefit to the grid. There's capacity, meaning that you are replacing a generation plant and the ability to generate power when you need it and where you need it. You can provide flexibility, which means that you're able to actually moderate the grid and make sure that you can balance the supply and demand at any given point. That's very important for renewables. So flexibility and capacity together are very important against renewables, because renewables don't necessarily provide the capacity, because you can get the energy, but you don't necessarily get it when you need it. And so storage matches that. And then flexibility, same thing. You might get a lot more energy, or you might get fluctuations in the renewable energy, and storage can provide a damping effect, which is very important. Reliability, that's actually the most important purpose of storage today, backup power. A lot of people use it for that. And then power quality, maintain voltage and power quality. And so that's a very important part of it. So mostly when we have these benefits, we often stack them You've heard about the value stacking. These days, value stacking is almost a bad word because it's almost a hackneyed term. You've heard it so often that it's taken for granted. But the idea is that no individual benefit is good enough to actually make to justify your storage system. So you want to add multiple benefits. And so the question is, how do we do that? How do we size the storage system to do all of those things? Where do we place it to get the maximum benefit? And how do we dispatch when we actually operate? And those parts are really all about what we're looking at when we're looking at potential benefits. So looking at this from a high level, I'm going to look at this as the grid, because the grid is a very complex machine. We call it the most complex machine in the world. And the way that the grid has evolved these days, you have centralized generation on the left side there, and you have loads on the right side, and the centralized generation generally feeds the loads through the transmission system and the distribution system. And so the question is, where do you put the storage? Do you put it on the centralized side, or do you put it closer to the loads? And the answer is, like we said with refrigeration, everywhere, all along the supply chain. And so we have bulk storage up at the high level, those things like pumped hydro, or things like, right now it's mostly pumped hydro, but in the future it'll be other technologies. You'll have distribution storage along the transmission distribution lines, and then you'll have customer-sided storage behind the meter that you may own and you may use to moderate your own energy usage. And so each one of these areas has its own set of values that it can use. Transmission level is most of the things that you usually think about as going into an energy market. So in California ISO moderates certain things on the grid, and it does that by allowing its generators to bid into a certain sets of markets. Energy storage can also bid into those markets, and that's what all of these services are, to make sure that the grid operates the way it's supposed to. And so it's typically an alternative for generators or for transmission assets. At the distribution level, closer to home, it's a little bit different. This is still a utility application, but typically what you're doing here is adjusting the way that the utility operates the grid, or the way the utility actually plans and builds the grid in order to reduce cost. The last mile, these are all last mile applications, and right now, at least today, the way they operate, most of these are done, are relatively.
He served a key roles as scientist, supervisor, office manager, deputy chief, and also the senior engineer. Currently, Mike is the senior engineer and also the team lead of the Energy System Research Office and the Energy Commission's R&D division. With that being said, Mike is going to provide a presentation on energy storage, which is funded by Energy Commission in last 10 to 15 years. So he's going to share a lot of upcoming opportunities on energy storage in California. Let's welcome Mike. Good evening.
Thank you very much, and thank you all for the opportunity to speak today. It's been interesting, considering the fact that three speakers did not get a chance to talk together, how diverse the topics are, and mine is also significantly different, but it is on energy storage, and so I'm going to basically talk a little bit more detailed about technologies and what's out there, and then also what's some of the big changes that are coming in the marketplace for everybody. And I'll start off by just, we mentioned before that lithium ion is the technology of choice right now, and I'll share some reasons that concerns me, but there's a reason for that too, I think, and I go back, it's my personal feeling, I've been involved in this since the very beginning. In the R days, they were worried about electric vehicles, and the technology of choice back then was nickel metal hydride. And the government spent $1 billion to improve manufacturing process, and lithium ion was the technology they invested in. And I think Tesla today would not be here had they not made those investments. And we wouldn't have cars that have a potential range of 200 to 300 miles, as opposed to the current cars you run into with a 40, 50 mile range. So that investment in the past made a big difference. And we'll talk to you today about another investment that's that large in California. California is going to be the largest energy storage market in the world and in history over the next 3 to 4 years. So for just a quick, what we do, so I work for the California Energy Commission. I have been there for 15 years, and I have been fortunate to do a lot. So right now, I've recently moved into an area where I spend most of my time on energy research and managing agreements and setting up new agreements and working with people like Chan to help them make the transition and do these types of jobs. So we're fortunate to get about $120 million a year in electricity research, about $20 million, $25 million a year in natural gas, and we get some funds like cap and trade funds to do work also. So there's a substantial amount of resources that we have access to, and we're able to use those to do different areas. And this is a full spectrum, not just energy storage, but we flow for the full spectrum of energy services. Also, we respond to state policies. And so the first one, of course, is 50% RPS. Now, interesting things have come out recently. There's been announcements that we're going to make that 50% way ahead of the 2030. This is the last year for Governor Brown. I haven't seen it, but I heard he came out with an executive order yesterday that we're going to have a goal of 5 million vehicles on the road by 2030, 2035 timeframe. But that's not unexpected. There's a big growth, but it makes a big difference in the energy storage industry because all those vehicles are going to have batteries in them. The other thing is the RPS of 50% is very likely will go up. My gut feeling is by virtue of us reaching that goal early this year. Last year there was a bill to go to 100%, which is kind of aggressive. I think something like 60, 70, 80% is reasonable. So I would be surprised at the end of this legislative session and when Governor Brown leaves that we will not have a higher RPS than we have today. And that will also drive the need for more storage. I will talk about the storage mandate because that's the big driver right now. Recent bills for energy efficiency improvements, zero emission vehicles, and also just to clean energy. We have focusing a lot of attention in California and underserved and disadvantaged communities, trying to bring these technologies to them. Our research is basically in the area from a prototype to a commercial system. We don't do basic research at the commission, so we allow people to start, except for our small grant program. I'll talk a case in a little bit later where we had an individual storage company take a $100,000 small grant, build a battery in their garage, and it worked well. They took the final report and sold it to venture capitalists like Jason. They gave them money. They then got a large government contract, and in the last 18 months, they've collected over $50 million in additional investment funds. So in the last 6 to 8 years, they've been extremely successful. We have another 2 or 3 contracts with them, and they've been doing very well in the marketplace, and I'll show you a little bit about them as we go forward. So the duck curve, again, the thing about it here is this is a net curve, and what it tells you is in the morning time, as solar comes up, the generation and the load mixture changes, and so you need storage to be able to absorb that difference. And in the evening, as the sun goes down, it's a reverse story. In the middle of the day, you have this overcapacity, and then in the, see if I found it, okay. And this time here is you have the peak differences. What this shows you is a change in energy. One of the things we talk about is frequency response. So one of the uses for storage, in fact, is just giving energy, taking energy on a second-by-second basis as this load changes. The ISO in California, Independent System Operator, and the rest of the country, it's called a regional transmission operator. It's their job to keep the grid running at 60 hertz. And if it gets off, then everything falls apart. I mean, so they're talking about like within 1,000th of a percent, not very small changes. So they're doing this constantly. Our ISO spends about $500 million a year buying these frequency services just to keep the grid on scale, in addition to buying services in the longer term. So that's one of those markets that you'll talk about for energy storage going forward. Just to clarify things in energy storage in general, we're talking about electricity storage, so you store electricity and you deliver it as electricity. Things like you got the process storage, you can take a big plant, a wastewater treatment plant that uses power, and you can cut the process down and the load will drop, and you can increase the process and the load will go up. It's more like demand response than it is, or load leveling than energy storage. There's a big industry now trying to convince the community that hydrogen in a tank is the same as electricity in a storage battery. The PUC doesn't agree right now, but they're still trying. So hydrogen is a very flexible fuel, but you got to put it through something to create electricity. So for all these discussions today, electricity in, electricity out is what I'm talking about. So this is the big change that's coming. Those of you who are not familiar, there's a bill called AB 2514 that's been around for quite a while. The PUC has done the first 2 years, I'm sorry, I hit the wrong button here. So the 14 and 16 procurements have occurred. 470 megawatts have been procured and are being installed or installed. In the next, this year, 18 and 20, they will do another $850. However, there's a change. There's another bill called 2868, which says not only are you going to buy this, you're going to buy 500 more megawatts. So now the PUC is going to direct the utilities in California this year and in 2020 to basically buy 750 megawatts of power. If you base it on what they've done so far, in the first roughly 500 megawatts, the average was 4 hours of storage. So we're talking 5,000 megawatt hours of storage to be procured in roughly a 2 to 3 year basis. That's coming. This is legislative directed, it's rate based. Money isn't an issue, it's a matter of getting the best value for your dollar. The second thing is the PUC has decided there's a certain number of applications that's acceptable. These are use cases. So when the utilities buy these storage, they have to buy them for this certain case of use cases. And one of the things I'm trying to find out from the PUC is if there's going to be some type of required leveling, or that if they could all buy it all for reliability. I don't know the answer to that, but the point is the utilities cannot buy the storage unless it meets one of these applications. So what I want to do now is go through pretty briefly the technologies that are out there. So one of the things that I do, and I'm briefing our senior management and other agencies on, is for this procurement, if we look at history, lithium ion is the battery of choice. However, there are challenges that are occurring. Jason mentioned it. If you look at the history of testing, a lithium ion battery will deteriorate 2 to 6% a year, depending on the technology and the manufacturer. So over time, you're going to lose power in that battery. You either replace it or accept a lower level. And other batteries don't do that. And as Jason mentioned, you'll see up here, we also invest in Amber Kinetics, and they're one of our success stories. We're happy with them. They do not. They can perform as many transactions as you want, as long as you want, and it does not deteriorate from day 1 to day 200. There's a contractor that was awarded a lithium-ion battery, 20 megawatts for 8 hours, or for 4 hours, 800 megawatt hours, and they signed a 20-year power purchase agreement with the utility. And they said, and I was talking with them when they were presenting it to a group from India, and afterwards I said, well, obviously, if you're going to use lithium ion for 20 years, then you've got some type of maintenance plan into your 20-year cycle, because he said, we're going to deliver to save 80 megawatts in year 20 that we're delivering in year 1. And they said, yes. So, I mean, there's potentially a substantial amount of that cost that they, of course, isn't available, unlike here, we're showing cost. The cost that the PUC pays is not public, not for at least another 5 or 6 years. But the point is, knowing the technology, knowing the commitment, no company is going to sign a commitment unless they've got a maintenance plan, a replacement plan, and they're comfortable in the year 20 that they can deliver what they say. And so there's probably a significant amount of cost, and those costs are higher than what you probably heard from Haresh from that perspective. The other thing I've learned in general from talking for this analysis I'm doing is with Department of Energy, is if you look at a power purchase agreement versus an own and operate agreement, as I understand the direction from the legislation, the utilities can own half of the systems. The other half, they have to sign third-party agreements, power purchase agreements. The cost of the two, from what I've learned in general, is about 50% more. If you take a 20-year cycle and say, what did it cost me for 20 years? It costs you 50% more to do a power purchase agreement than it does own and operate it based on analysis. And those are just numbers I get from DOE, but it's not unreasonable. And the second question is, how much uncertainty do you cost in that 20-year contract? But the point is that there are probably much more extensive prices for those 20-year, and again, the PUC and all of us will be paying those prices as we go forward. The other thing besides just those applications is microgrids. We have 7 systems that are operating. All of them have energy storage. We're in the process now of evaluating $45 million in microgrids, about 8 to 10 microgrids. All of those have energy storage anywhere from a few hundred kilowatts to a few megawatts. So it's one of the applications you'll see these technologies I'm talking about on a routine basis. So we've been fortunate. I've been fortunate since I was actually hired to commission because of my energy storage background. We've been fortunate to work in everything from customer-side storage to grid-side storage to transmission-level storage. Up the upper left, right here, this is compressed air, hundreds of megawatts, pumped hydro, hundreds of megawatts. Obviously, Amber Kinetics here we're talking about is in the megawatt range. This is EOS, which is another technology we'll talk about. premise power. Here we're looking at lithium ion systems. The other thing that's important to understand, if you'll see these three here, the industry has kind of decided that the cheapest way to ship and install these things are in these containers, either a trailer or a commercial commission trailer. We had some projects, and I'll show you one, where the flywheel company was going to build a big plant. They built the flywheel in a trailer that was 100 kilowatt. They want to go to 20 megawatts, and they're going to build this big building, put everything into it. They didn't do that. They ended up with 20 flywheels, 20 trailers like this, with each one holding a megawatt, because that was much, much cheaper than building and maintaining it. The application side, just to show you, in our experience, we've been fortunate to pretty much operate and test all the technologies that are out there, except for the very newest ones. So we've been through the full spectrum, and we have projects, and we will continue to expand as we go forward in those areas. So we've got the opportunity to understand these different technologies, how they operate, in most cases in a demonstration or a laboratory environment basis. And you've heard earlier, this is the national, but the California picture is the same. We've got about 4,000 megawatts of storage on the grill. 95 or more % of that is pumped hydro. The small percentage of it is that. Now that's going to change as if we put in 2 gigawatts of non-pumped hydro, then that little piece will change. But right now, the bulk of the storage in California is pumped hydro, and we are rapidly adding to that mix. This is actually a price chart that came out of a couple of presentations. One of them included Department of Energy, and then up here you can see the different people showing. So there has been I've been involved in storage for 25 years, and in the last 5 years, I think there's been more improvement than the last 30 years. And both because I think what amazes me in my job, I get asked to brief people all the time, I see visitors all the time. There are people who are non-technical who are asking about energy storage, whether they be a commissioner or a legislator or just a visitor. They're asking, they hear about storage and want to know about storage, and they're asking the questions and they're interested and they want to do so. Storage has reached a point where it is a topic of conversation to lots of people, and as a result of it, it's just becoming a very predominant area right now. But there has been a substantial cost increase. I think it's going to continue. Another tidbit I'll bring up here that I like to point out in this area is I read an article once about PV, renewable energy. When it first invented, it gave me the first one is 1% of the cost. It's come down 99%. So now storage isn't that way, but those types of savings are realistic. The other thing we talked about again, and in most cases, is the balance of plant. I have a lot of new storage inventors and entrepreneurs come and talk to me about the marketplace because we're public, we share everything we have. And I can tell them, you can give the storage away. Your storage could be zero. If you don't manage the rest of the cost, it's still too expensive to sell. And so the other analogy I have is in the renewable market, the PV market in particular. Most people know PV prices are really at a record lows. There was a time when the price effort and all the research was on the panel, making the panel cheaper, making it produce higher energy for same square footage. Then it shifted to the balance of plant, putting the system in, permitting it, safety considerations, and all these things. So in the renewable energy, they brought both of those prices down to where they're both at a very reasonable, comfortable level now. Storage is getting to the point where it's now saying storage price is coming down. We got to focus on these other costs, and they're clearly able to get down. Now we're doing things to help, developing guidelines for permits, developing guidelines for installation, for safety guidelines and things. So we're trying to do things, lessons learned and guidebooks. So clearly there's an area that storage will benefit over the next 5 years because it's just the way as you look into doing it and begin to focus on those costs, you can bring those costs down also. So what we'll go through now is talk about technologies. I'll show these two technologies here because they both EOS and Amber-Kinetics received orders from PG&E in the first round of the solicitation to deliver 10 megawatt and 20 megawatt order for 4 hours. And so we have invested in both of them. We have current contracts with both companies where we're doing demonstrations currently with them right now. PG&E is looking over our shoulder and is on our advisory group. This just shows one of the examples of EOS technology. So again, just to mention, it's a hybrid zinc cathode technology, and you heard about Amber-Kinetics. So this is just showing an example next to a solar farm where they've got a system. Here is some of the field work that's being done for Amber Kinetics as they build their next prototype systems. And that's the kind of stuff we invest in as next generation improvements and doing things to improve the cost or improve it or to validate the performance. One of the things that Haresh mentioned that I also agree with, that is long-term testing. One of the challenges I have for lithium ion is there's a lot of information known about its operation in a vehicle. There's very little known about its long-term performance in the stationary battery mode, particularly 5, 10, 15, 20 years out. And it also has some thermal issues as well as potentially some issues with chemical composition. One of them is cobalt. There's a problem right now with cobalt, and since the price has gone up 3 times in the last 2 years and another 100% this year, it has some environmental issues or environmental justice issues where half the cobalt comes from Congo, and the perception is that 2/3 of the manufacturers are the miners or kids out there with their hands and knees pulling cobalt out of the ground. So it gets a point where it makes a difference, and so it could make a difference in the supply chain. Particularly if we talk about a large number of electric vehicles at the same time we're trying to buy batteries for the storage industry too. That's where you have a supply and demand challenge. Primus Power is the one I mentioned. They actually started with the garage with a small grant. They received a second grant from us, and then they got a large grant from the Department of Energy, and then they've gotten several commercial grants. They've been very successful in the military market. And then this is a flow battery, zinc bromide flow battery. If you're not familiar with flow batteries being different than a fixed battery, they basically have tanks and here, so it flows one way when it's charging and it flows the opposite way when it's discharging. You want more storage, you just get a bigger tank. And it's very straightforward. Does not have the same issues that fixed batteries have, where they don't have a lot of deterioration, they don't have a lot of issues, but they do in some cases have chemical issues. The chemicals are not benign, but they still have to be controlled. So if you have a tank that leaks or something, you have some environmental issues at work. So it depends on which particular. This one here is a vanadium redox battery example. Here's a company, UET, that's doing a demonstration for us at one of the university campuses. They are doing flow batteries, as we saw right there. This is another company that's doing a project with San Diego Gas and Electric. Sumitomo, they're doing a vanadium redox. This is a 2 megawatt 4-hour demonstration they're doing down in the San Diego area. Sodium sulfur, you may have heard, this is the one that's been around the longest. I was involved in this project probably 12 years ago. It took PG&E about 6-7 years to finally install it. So they purchased 6 megawatts by 7 hours. So this particular technology, 1 megawatt, 7 hours is their module. But they ran into all kind of problems, so they installed it at 2 sites. There's at Vacaville here, if you drive back to Sacramento, right there is a 2 megawatt by 7 hour system installed at Vacaville, and there's a 4 megawatt by 7 hour system installed here in the San Jose area at one of the manufacturing plants. But both of them are up and operating. This particular one's been around the longest, but also in the big picture of things is the most expensive of all the technologies you've seen so far. So they haven't really had a lot of aftermarket sales in California because the pricing is substantially higher than their competition. Lithium ion, there's several vendors that do lithium ion. There's only about 4 or 5 manufacturers, and there's probably 100 vendors that are selling lithium ion because that's their battery of choice. They just go and get a competition amongst the manufacturers and pick who gives them the best price. I brought this up to one of the commissioners, I don't have the picture here, but I brought one of the commissioners at PUC. I was getting a brief on them back last fall, and I said, you gotta understand, lithium ion, it wasn't that long ago, lithium ion was burning up airplanes and burning up laptops and burning up cell phones. I said, the technology is the same. You learn 2 things when it comes to managing it. One, manufacturing process. If they take the time to do it right, you can control the thermal runaway. If you rush the manufacturing process, the thermal runaway comes back to bite you. The second thing is the cooling process. You have to be sure the battery's cooled properly when it's operating. And so what happens is just in November, there was a large lithium ion system in Belgium that was being commissioned and caught on fire and burned down the whole substation. And so that they continue to be a challenge. So it can be managed, but it needs to be managed. And so when you're buying large quantities of that, and if you go out for the cheapest bid, then you put yourself in an environment where you may be running into challenges in the future. Now, I can't talk about lithium ion. We'll talk about Tesla. They have a good market. Because even though I noticed, I read an article yesterday that Tesla said they're having production problems and they're manufacturing their batteries by hand now because their production line is shut down. So it's obviously they're having some challenges too. This is the Santa Rita Jail, which has been won national awards and state awards. Obviously, a jail has a very high load, so the jail has installed a microgrid, which includes a lot of storage. And the main reason is to reduce cost and increase reliability, and they wanted to lower their carbon footprint. So they were able to do clean energy as opposed to just taking stuff off the grid. Flywheels, there are several types. This is one that was being installed at Pendleton Marine Corps Station. They did a couple demonstrations there. This one is about a 100 kilowatt hour battery that runs for about 2 to 4 hours in there, supporting their microgrids. The other one I mentioned, we did a test with these guys. This is Beacon Power. So they came out and did a 100 kilowatt test with us in a system where they had 100 kilowatts in a container, and we had it certified by the ISO to operate frequency regulation. So in this case, they went back in New York and back into New Jersey and built this one. So there are 20 trailers. Each trailer has 10 flywheels. So it's 1 megawatt in each trailer, 20 trailers, as opposed to a big room with a roof on it. They just become much less expensive. They actually have 2 of those operating back in the East Coast. But this is also operating for 15 minutes. So it only provides frequency response. It doesn't provide a bunch of other services. They only have 15 minutes worth of stored energy. And so they're focusing their attention on one market only. Just a couple more things. Compressed air. This is a picture of PG&E at one time with DOE funding was going to build a 300 megawatt compressed air system in California, but they've no longer, they basically have backed off on that. They did some research, they did some design, my understanding is that it's on hold or they're not going to do it. Here's another, I think you saw some of the charts, an advanced compressed air system. Here's an example of Hydrostar where they do a compressed air, but they have a unique way of building their own caverns and a unique way of processing it that provides higher efficiency and better cost effectivity. But this one is in the prototype stage. They're doing their first prototype now. And then this one here is what's called liquid air. They're building a system. This one is basically using compressed air above the ground and freezing it for liquid and then decompressing it. And they've got a system that they're building that's supposed to commission next month in the UK. That's 5 megawatts for 15 megawatt hours. So this is just, again, so that in some cases you're looking at storage at small scale. In some cases you're looking at the replacement of a power plant with as you mentioned, is a storage system that looks like a power plant. The other thing is vehicle to grid. We have a goal right now of 1.5 vehicles on the grid, electric vehicles on the grid or zero emission vehicles. And if you add it all up, it's about 6 to 10 gigawatts of storage. And so the question becomes, are we going to use this storage like in vehicle to grid applications and smart charging applications? So are we going to use it to help the grid, or is it just going to be a load? So we're doing research to make vehicle to grid work. We've been funding with the Department of Defense the largest vehicle to grid demonstration in the world at LA Air Force Base. There were 45 vehicles going through testing. So we've been trying to figure out the best way, smartest way to do vehicle to grid. Because at the end of the day, with this many cars that potentially can go out there, if the auto industry can get a 300 to 400 mile range vehicle that's electric, then the market will change. When you have to get a car that's 100 miles or less, it's got different visibility. When you get 300 to 400 miles of electricity range, then you open up the market for most of the customers who use this car. Just a quick summary here. This just shows you the number of people that are out there. There's quite a few. So one of the things I'm trying to talk to our agencies about is as we go forward with this procurement, that we do technology diversification as opposed to just going for the lowest cost. And also look at a performance, look at a 5 or 10 or 15 year window, not just in performance, not just a short-term window of the first price and out the door. So this is just a study. New slides are available. You're welcome to have all these slides when we're done. The other thing we've done is some testing and we're doing some work. We did this work with Lawrence Livermore National Lab. We studied the grid. We've done a study before with KEMA, and we did 6 runs, one each season plus 2 other runs to do the analysis. With Livermore's supercomputer, we did 30 runs a day all year long. And they were able to go through and look at how the batteries charged and discharged. So when you got 2 or 3 more gigawatts of storage on the grid, that becomes a bigger issue, how you charge and discharge all those batteries as opposed to just letting them charge at their own rate. The other thing is just looking at how you manage the peak demand, different type of technologies, and how much it can play a role. We will be doing a fairly large study this summer looking at the grid itself, looking at storage, looking at where is the ideal place to put storage by its size and its duration. So that if you have 100 megawatts that you put it in one location, 3 locations, you need 2 hours, 12 hours. So we're going to be doing some pretty complex modeling to give the PUC and others information about how to plan. It won't be available for the 18 procurement, but it should be available for the 20 procurement, for them to use it to help them make decisions on what size of system they want to buy and what type of duration they should be asking for. And that's it. So I think, unless you wanted this question, this is the ones that you have. Everybody's ready for a break.
Just wondered, you mentioned earlier in your presentation about, I think you were talking about build to own systems versus the PPA system, where you said the PPA price was higher, and I just didn't understand why that was, unless there's some costs to the PPA price that weren't being factored into the ownership model. Or just wonder if you could elaborate on that example.
So I think I heard the question. So I mean, looking at the cost versus PPA, it comes down to a question of analysis of owning it and operating it, who's going to do the work or who's going to manage it. So for example, in this case, do you just buy the system and then program 20 years of maintenance and recovery on it, or do you sign a contract that takes care of all of that? And they're doing both. But all I'm saying is the analysis I've heard from DOE, you have to look at specifications, but when you do it generically, it works out, and their number is about 50% higher to do a PPA than to do own and operate from a cost perspective. Again, that's based on certain maintenance numbers and certain losses with the system. So obviously, you mentioned the example earlier, if you have a system that has no losses and it operates year 20 the way it operates in year 1, there's one system. If you have a system where you got to swap out the batteries twice in 20 years and you have to do maintenance every 6 months, there's a different cost. But in general, the PPA is built in with profit, is built in with contingency and everything else, so that there's typically a higher cost. But you don't have to have the hassle with actually doing everything. And again, like I said, as I understand it, there's a certain amount of procurement that has to be third-party PPAs.
A question about the storage. After a while, for example, like 10 years, you want to swap it out. So where would it go?
So, I mean, that's a disposal question. So one of the issues, I mean, I think Haresh mentioned was recycling is one question, reuse is another question. For example, is that we're doing analysis right now on electric vehicles. Typically, a battery lasts 5 to 7 years. It's a power requirement. In other words, you push the gas pedal down, it's got an acceleration, but it's got a lot of energy left. So we're actually evaluating how long can you take those batteries out of a car and put them into a stationary system for 5 or 10 years, and how will they work? As far as the technology, if it's a flow battery, then most of the chemistry is just chemical. And when the battery's up, you just process the chemicals, however you do it. And Haresh has a picture. I usually show it, but I took it out of this one. So we worked with DOE on a project for a flow battery. It's a great picture. I consider it one of the best storage pictures I have. It shows a 1 megawatt system right next to a nice wind farm, and it's supporting an almond production farm, so it's all the pumping loads and everything, and it was $6 million for BOE and $600,000 for us. There's nothing left, it's all gone. The company went bankrupt or insolvent, and they sold everything for the value of the hardware or the material, and they took it all out. And the only thing left, I got a picture with people saying that's to a system, but the only thing left is the concrete pad. Everything else was removed and sold because the company doesn't exist anymore. So one of the challenges in storage companies, when you look at a 20-year view, and we've had, in my experience in the last 5 years, we've had maybe half a dozen companies, either one go insolvent, or two say we're not going to do this anymore. We actually turned down their contract. They got a grant and said we don't want it. We're not going to do this anymore. If they're a bigger business and they say we're going to close that business unit down, or the company has some type of problems. We had a flywheel company that had an accident that was terminal for that company that never recovered, and those types of things. So there is always that, when you're a small business, making it to the first 5 years is one threshold. Making it for 25 years is a different threshold. So when you're talking about a 20-year contract, one of the discussions that the state has to have is, what do I do if this company isn't around in 10 years? How do I protect my system? How do I do it? We're getting ready right now. We did a system that did CO2 washing of clothes, and it was even the military was evaluating. It's on a military base, And we were doing things because you could wash Kevlar vest and military gear and not damage it. If you take that Kevlar vest and put it in water, the bullets go through. But we were testing it, and they were going to actually take the stuff to the firing range and check the bullets to be sure the vest continues to stop them. Literally overnight, that company decided to shut down, and they just went away. And we have this system, and the Navy doesn't want to maintain it because they don't know anything about it. So we're going down in a few weeks to do an assessment, and we're going to have somebody come in and take it out and sell it for what the materials are worth. And that's not uncommon for us to have to do. I mean, when you invest in, there's a research element where you do this. But if we don't take those kind of projects, then we're not really getting the best opportunities. So there's a price for doing research. When research does it, you learn a lot. You actually can learn sometimes more from systems that fail than ones that are successful. But we do have examples, and I certainly have been involved in enough of them, of projects that I was very hopeful for, where it's just whether it's the wrong CEO, whether they just couldn't handle the marketing right. I mean, we thought the project had a very good opportunity. It's just they didn't have the orders they needed. That's one question, and for your benefit, I always ask, every time we have an order in storage, I sit down with the CEO and say, okay, what's your next plan? This is good. What are you going to do after this? We're not going to keep giving you an order every time you ship it. You got to, what's your next thing? How can we help? I mean, we do that. We have conferences. We introduce companies to venture capitalists. We try and do things to help companies be successful. Our charter from the legislature is to bring more commercial products, environmentally clean commercial products, to the California market. That means they have to be successful companies. We want those companies to do well and sell products and pay taxes in California. But, so we are allowed to help companies that we do contracts with to be successful, but it's also a point where it's in their hands, the company growth, and I'm sure that you guys, I've heard rumors that most venture capitalists, if they get 2 out of 10, they're doing pretty good. So that means 8 of them don't make it, don't get to the profitable point.
We're failure-based business.
Anyway, so I'm going to let her have the break, and I'll be glad to
I
answer
have
questions.
one question.
Yeah.
So the California energy storage is driven mostly by policy of the legislature. Would public utility allow to set goal for themselves if there's no policy driven?
So the public utilities have, I'm saying in general, so in California, the utilities, it affects everybody, so they have to do a storage mandate, and it's so pronounced. When this is over, yes, they will be doing what they need. We're anticipating, they're not putting storage on the grid because it's failing today. It failed in 2000 and 2001, and we lost the governor because of it, and nobody wants it to fail again. So we're being very forward-looking and addressing the issues of all the duck curve and everything else. We're trying to address all these issues in advance, so the grid. Now, the truth has been, all of California's aggressive environmental changes have not made a substantial increase in rates. We have not had a rate revolt or anything, so the rates have increased, but not substantially based on the services. So they've been doing this in a manner where they've been able to swap out systems at a relative cost. And the grid, at least from what I've seen so far, the grid cost has not, there was a Bakerfield revolt, they called it because of the smart meters. They put the smart meters in and everybody's rates went up because of the way the meter worked. And they had a revolt. People just literally revolted to the PUC and said, I'll take this thing out. But as far as this, the grid cost and the cost of energy throughout California, there's not been, in relationship to the rest of the country and everything else, even though we're doing all this aggressive policies and aggressive installations and doing all these changes we talk about, there has not been a substantial increase in the rate to the customer sees. And so to answer your question in general, once the mandate is over, if the utility needs storage, they will buy what they need. My gut feeling is this procurement will end up with higher performing storage and less costly storage for the whole country.
So the question is, would they, after the mandate is over?
I'm sorry, what?
Will they buy? That's the question.
You mean right now or in the future?
In the future.
That's, I don't think anybody's thinking beyond the $5,000. I'm worried about this year or next year. You're right. I think in general, the question might be better, will the rest of the country buy it? And so we're talking with 5 other states that are learning from us, and they're developing their own energy storage plans, and all of them are going out to buy energy storage, every single one. So they're convinced they need to buy storage. Only New York has come up and said, here's our mandate. But the flow is, the value of the storage and the need for storage is beginning to be seen in a lot of places, and people are beginning to do that. So I think in the perspective of growing companies, the market will continue to grow. It will not just be this one bubble. This bubble will be a big opportunity and will consume a lot of manufacturing capacity.
How about let's
Use metering going mandatory to everybody is still on the books for California in the next couple of years?
As far as I know, yes.
Well, that's gonna change people's
Could-
view
could-
of their electric
I
rate, and
don't-
if they don't have storage to do the refrigeration analogy, they're gonna be screaming that you're taking me for a ride, because
So,
you're.
I don't follow rate structures much, but my understanding, the PUC's decision in this year at some time is to shift everybody to time of use rates.
I think that's a ticking
And that
bomb,
would
and I
be-
think you're gonna find storage become an interest because of that artificial economy, if you will, that they created in that move.
I don't disagree, I understand it's become, I just don't know the impact, and all I know is you're correct, the PUC has directed, people can opt out, but they have to pay a price to opt out.
Yeah, it's not cheap.
And so, but again, that perspective, and then also I said, what I'm looking at is sharing what we're learning with the rest of the states, so they can make their decision, and they're receptive. And all of them I've talked to either have or are looking for money, they're getting tens of millions of dollars to go out and do their own projects. So every state that I've talked to, I'm working with a half a dozen right now, either has solicitation they've recently done, or they will be doing one, and storage is the topic. Thank you.
Great presentation.
And firstly, I'm late. I was thinking about how about we invent a voice storage technology. I didn't catch
That's
it.
called the tape recorder.
Exactly. So I'm saying it's like I missed the first part, and but the whole thing based on my observations, really very good combination of the three presentations. You can see, developers doing the research give you some bad news. However, for sure you're going to have the future expectation, and then we have some wonderful money there from the CEC to support this, to commercialize all these technologies, which is great. However, Jason's question kind of say, well, how can you give me a guarantee? There's no guarantee if your price is high. So I'm on behalf of the CPUC, let's say, anyway, just let's say that way, right? So I'm saying, anyway, but that's not the real issue. Here, I'm talking about the support from IEEE. I'm just kind of finished meeting this morning, that's why I'm late. And IEEE right now, we always, continue to support all these kind of activities. Very important activities. Really appreciate Wendy and Yazhou. All Huawei for sure. So to organize this event, to put everybody gather here together to exchange ideas. And I support that we volunteer for IEEE right now. We're going to continue to do that. And basically we have technical meetings in CPUC building, basically. This year we're going to have the meetings in another state building to facilitate the coordination and the communication and collaboration with all these people and the power society, let's say. So really appreciate that. And then you can, take a look at our organization. We're going to have more opportunities. And we also invite people to come up to our San Francisco to give us speech and then give us education. So we really look forward to that. I'm still having, the first month was Wendy. Did a presentation for us, really great. Talk about transmission and energy storage. So, and now we continue to do that every month in general, and then we're going to have a workshop on September. Currently, I thought about the power electronics, so as the one of the thing to talk about, and then for sure, last year we did the distributed energy resources. So today, this event organized by another IEEE chapter, but that guy didn't come here. I just say, hi, I don't have to come here to say something because we really want to support that, but because we're in San Francisco, there is a local chapter here. We don't want to step in, so that's why I just kind of say something here to really appreciate these efforts put together, and I really appreciate the presenters and to give us a wonderful speech, especially the three parts. I can see that perfectly matched together. Thank you very much.
Now it's a question, like a Q&A section, right? And this is an informal panel discussion. We didn't prepare like a anybody still has, based on the 3 presentations, any question you didn't get chance to ask after the presentation, please bring it up here.
Yeah, we call it a panel session, but because we didn't talk with the speaker before the event, and it's a little bit challenge for us, so we decided to buy one, get one free. So I'm the free one, and we are co-hosting this panel session, and feel free to ask questions, and also we can also ask questions, so make it informal, let's communicate.
Okay. So I think first.
Okay, yeah, I want to ask what's your forecast on how big the storage market would be in California?
So the question is to
Any of them, right?
So whoever has maybe some ballpark of the number.
What's the government number?
Okay. 500 or 1,300 mega, something like that.
Yeah, something like that.
Oh, probably.
Well,
That's it.
yeah, there's a number that in my presentation, I think it's 30 billion worldwide. But yeah, at this point, that's the research analysts are saying. But if you follow our discussion of TAM, if you take the total worldwide energy consumption, you can say 10% of that need to be in storage. That's a huge number. So you can, I'm saying you're a young guy, you can, work in that industry until time you retire, that's still there. Right? So it's a great industry to get into at this point, because any new industry gives you an opportunity to grow, and maybe you're the unicorn we're looking for. we're in the business of looking for a unicorn.
So we actually have had this question before. I had a storage workshop years ago, and people speaking about the need for storage and everything from 50% of the peak demand to other numbers. We did an analysis with Livermore for 33% renewables and using existing storage tariffs, which are not very friendly, and came up with a number of about 1.5 gigawatts, which is a little more than 1.3. With the 50% renewables and with the change in the electric, so my gut feeling is we'll probably end up with something in 3 to 4 gigawatts when it's all over with. I think 2 is probably sufficient for 50%. I think if we go above that, it's an exponential curve, not a linear curve, so the further we go, the problems get more complex.
So that 3 to 4 is for entire California.
Right. As far as a mixture, because the peak demand typically is around 40, 45 gigawatts in California. So you're not going to get 10 or 20% of that load at peak demand. It's more likely look at your average demand, which is maybe 20, 25 gigawatts. So 10% of that would be 2 gigawatts of storage. It is expensive, but there's a trade-off. But California does not want rolling blackouts again. But we're doing it in the ramp, and again, most of the stuff we're doing is in advance. We could get to the point where we say we have more than we need, but I don't think we're going to get there.
So that means the mandatory goal, which already show there, is that going to gradually increasing.
I think if we change the RPS goal, the mandatory goal will go up also eventually.
Okay. So it's kind of a parallel with renewable goal, RPS goal, and the energy storage goal is going at the same time.
A lot of this is very uncertain at this point, right? We're talking about relatively near term, in terms of maybe the next 10 years or 15 years. I don't know what time frame you're looking for. In Jason's point, some of the more extravagant projections are maybe, I think, not unjustified, right? If you think about it, maybe 10 or 20 years down the line, you could see maybe 10% of the grid being storage. If 10% of the grid in California is storage, then and say it's $500 a kilowatt, that's a $5 trillion market. So that's $5 trillion of capital, not a market per year, but that's still that's a, and if you're replacing 1% of that every year, then that's still a $50 billion market. So that's pretty big. It's pretty significant. But there's no guarantee that we'll get there to that level. We don't know what it's going to be. We don't know that storage is going to be that valuable. It's $500 a kilowatt. Maybe it's cheaper. We're still trying to figure out a lot of those questions.
So, is there any research is ongoing. For example, calculate if I have 50% of renewable, how many megawatt we need from energy storage, or if this is go up to maybe 80% of the renewable goal, and how many megawatt energy storage we need. So is there any research or something else?
So I did mention, we are going to do that. We've got a substantial amount of money in what we call the third investment plan. The funding has been approved by the PUC, but we don't get the money until July. So we are going to do a large model, multi-million-dollar model, looking at the California grid and looking at all the challenges and looking at storage particularly, and looking at how the size and location of it and different amounts of it to determine the locational value, the size value, the duration value. Because one of the questions I always ask, you know, are you going to buy everything the same, or do you want a mixture? Do you want some short, some medium, some long? Well, a lot of common sense will say you want the latter. You want a mixture of each. So in some cases you want storage that's going to last you through the night. In some cases you want storage that's going to respond right away, if you're going to do it right. So I mean, I believe when we get done with that work, it'll come up with a mixture that says you need a combination that's of some value. But right now, most of this is being done by what I will call back of the envelope computations. There's no real analysis I've seen to give you an answer to that question of how much is too much or how much is not enough. We're just hoping we don't get to the point where we made a mistake. The one thing about storage is you can't buy it tomorrow. It takes time. It takes years to put in storage, not days. You may have heard in San Diego they did an order because of the San Onofre problem. I mean the problem with the Glacial Canyon, and they were able to develop an order, get a PUC approval, sign the order, and install the system in 90 days. Cool. So it was great.
Wow.
Well, but the truth is, if you ask the question, there was a reason for that. Somebody else had bought those batteries and canceled the order. So there's a vendor sitting there with a warehouse full of batteries ready to ship. And man, their ship came in and this guy's bought them right away. So I said, yeah, but we can't do that tomorrow because nobody's sitting there with the 480 megawatt hours of batteries sitting in their garage, you know. So, but it was a case where they actually were able to get the thing approved, PUC approval, a contract signed and delivery in 90 days.
And that's unheard of, you know, in the utility industry, right? I mean, it's usually 18 months for a gas peaker, which is a very well understood, you know, process. You know? So doing something that quickly is very unusual.
I mean, the government red tape is about the 18-month cycle, or could be
It's
shorter?
not just government red tape, but I mean, you're looking at everything along the way. You know, you're talking about your environmental impact studies. You're talking about your, you're getting a gas interconnection, getting a water interconnection, getting the emissions permits. A lot of that is cut out for batteries because it's just another piece of electrical equipment. So you don't have to worry about gas. You don't have to worry about environmental impacts. You don't have to worry about, well, you do have to worry about environmental impacts, but typically it's on land that's already been, set aside for, your right of way. So it's very fast. But to Mike's point, it's a little bit unusual for vendors to simply have this equipment lying around, for them to install. And in fact, one of the things that we've benefited from in the cost projections that we've talked about for lithium-ion is the fact that a lot of these companies have scaled up their manufacturing in anticipation of a tremendous market in EVs, which has not yet materialized. It may materialize, but right now they've got these huge manufacturing plants that can churn out batteries very quickly, and they want to churn out batteries as much as they can, and so they have quite a bit of product available, which is quickly getting soaked up, right? So that's not always going to be the case.
Maybe I should ask you a question. So have you guys looked at a smart energy grid in the future with that impact energy storage?
So, not in the specific term,
Okay.
but we've done it informally, and we do it from a perspective of looking at different changes that are occurring. And for example, there's a lot of effort in our office looking at DR and storage together to make a combination as opposed to just storage or just DR. And there's areas of looking at how energy efficiency. So like one of the things, we have a big energy efficiency goal, and what people don't realize is energy efficiency is great, but it doesn't affect the duct curve, it just lowers the load. It doesn't change those ramps, because it doesn't affect the generation. So when you make these kind of changes and look at what's happening, you have to look at how it impacts the grid. And in some cases, it has no impact. In some cases, it makes it worse. In some cases, better. You've probably seen that we've had power plants that we thought were going to be approved that just got turned down and they're not going to be online. So now you got to do your projection. You know, the commission does a 10-year projection based on what's supposed to happen. And then when those things change, the projections are no longer exactly. Got to go back and relook at the projection. So what's happening that I'm seeing is there's more. There are transmission lines that were going to be installed that the PUC, the ISO has decided is no longer needed because storage is available and is enough to solve the problem. So they're not doing transmission lines. There are power plants, peaker plants, or small, 50, 100 megawatt plants that were going to be built that are being canceled because they say, we don't want to do that, we're going to do storage, or we're going to do renewable storage. So that's in California, so there's a change. And so there will be an impact, but we won't know that for a couple of years. And so that's what we're trying to do now, is to take a look ahead with the primary focus, because storage is the most flexible response. You can do demand response, you can do efficiency, you can do generation, you can do different things. But storage responds fast and recovers fast. So if storage can do it, then you can find an alternative, but if you don't have storage, the alternatives can't do what storage can do. And so when you're doing modeling like that, if you can come up with a number, and you can go back and say, okay, how can I replace that with something like demand response, or how can I replace that with TSP? There is a shift to more and more distributed resources, which also changes the complexity of how you manage the grid. So I mean, to answer your question in general, I'm not aware of anybody doing those kind of studies in any detail. There's been some discussions, and this comes up when we have we do what we call the Integrated Energy Policy Report every 2 years, and we have sessions where people come in and say, these are the issues that you should be addressing, and so we address those issues in that plan. So these topics come up when they look at resource adequacy, when they look at availability, look at environmental concerns and things like that. The decision's been made, or at least recommended, to not react and to close down Aliso Canyon, which was the biggest natural gas storage area in the country. When the PUC looks at a new natural gas line, they have to look at alternatives, which includes, don't do the line, let's do storage and not do the line. Let's provide electricity versus natural gas. So all those considerations are being done. In the past, they were kind of just like blown over. They did them, but they didn't look at them. All of a sudden now they're becoming serious, and all of a sudden they're saying, well, we don't want to put that pipeline for 100 miles. Let's do this instead. And so there are, I mean, storage, I mean, my experience of being in storage a long time, storage has more of a place at the table than it's ever had before. And I think other states, I've mentioned before, we work a lot with other states, and other states are starting to be interested. I don't think they're going to be as aggressive as California, but they're going to be more aggressive than they've been in the last 5 years. So I think there will be a market expansion and growth in general, simply because people begin to realize they need to begin to put this capability on their grid, so when they need it, it's there. Doesn't mean they need to go buy 1,000 megawatts, but a couple hundred or whatever it may be in certain areas, and they're planning ahead, and they're looking to encourage industry and do things like New York does, where they do the research, and then they try to get the venture capital community to pay for the system, and make money off of it over 20 years.
So a question to Dr. Xu. So you are a partner of a venture capital firm, and the storage company is only one of the type of companies in your portfolio. And what difference do you see between investing energy storage company, or even broader, the renewable or power industry company, and compared with other industries?
Oh, yeah. Actually, it's a very good question, because 5 years ago there was a lot of money flowing into clean tech energy industry. Solar, we're talking about the dirtiest production, the stuff that now you see on top of your food. Actually, there's a lot of pollution for manufacturing that thing. And if you look at it, and then there's a lot of money goes into a thin film for solar. First Solar and what else? I think there was another company. There was no, there was a Mia Soleil,
yeah.
Nano something, Nano Solar. So there's a lot of money flowing, and the industry, what I call it, VC industry, lost a lot of money on that investment. So we have to understand how the VC industry works. We works in maximum 7 years. A fund is typically 5 to 7 years. So by the time the fund matures, all the money is invested, and then they go into a mature stage that you have to harvest. And if you're not, they just, end of 7 years, everybody just say, forget it. We just sell the shareholder in a company we leave. And so that what do we call it? That fund is closed, right? So one of the biggest things for us is the energy industry is long cycle. It's not suited for us. It's a very long cycle. And if you think about the Amber, it started 2009. Now it's almost 9 years. And the reason we stuck with them is because we stuck with them. And they turn out to be great. We love it because then we have to figure out where the money goes and where the money coming from, this fund, that fund, and we're going to do a lot of stuff. So that's really an impact for the industry. Now, you have to understand this industry is coming from the internet. And the internet is different because you can have a team of 3 guys and 5 more, and you have in a year or two, you have explosive growth. Right? You have Airbnb, you have what else? Uber. Those are computers. They don't own any Uber cars. They just own a platform. So that's an entirely different business model. So we have to change. In order to invest in the energy, we have to have a longer fund, which is not happening at this point. So our industry has lost a lot of money. What I heard was 50% of money is gone.
Just 50?
Still, I think there are Amber out there that are holding our money. So whenever you get bitten, you don't want to make the same mistake twice. So that's why you see recently I'm a mentor for the California Tech Open. I remember 7 years ago or 5 years ago. It's very popular events. I go there, and there's a lot of small companies doing generation, solar, environmental pollution, all kinds of stuff. Very interesting, and they all moved to China now. I'm sorry, I can't find them because I was just looking at them. And California Clean Tech Open, they had the same events, but in LA, so I didn't go. But just money is dried up. So that's really the issue. So we got an issue that we need to face is one is the long cycle, the other one is money dried up. I know that 5 years ago I saw a compression air storage company. I think they're gone.
No tears.
So this is from a VC perspective. This is a high risk.
Absolutely.
High risk, low return.
High risk.
If I might add something on that. So, the thing is, you have to remember that there are multiple, we're here in Silicon Valley, and so when we think of investment, we automatically move to venture community. And as Jason said, I think that this if we look at hardware, if we look at storage hardware, this is really not the business that most VCs will want to be in. Especially right now, because now you're going to compete directly with the Samsungs and the LG Chems of the world, where they're throwing in billions of dollars and trying to do this and competing in competition with each other. But there's more to it than just the hardware. The control systems are very important, and understanding how the control systems interact with the markets is a key part of storage that is right now not getting as much attention as it should, mostly because the hardware is not going in there. So, but once the hardware is in place, once we start seeing deployment, we're already starting to see deployment, starting with lithium ion, maybe other technologies down the line, then the control system becomes very important. And we're starting to see a little bit, not but a little bit of VC investment in those software companies that are trying to find just a better way of controlling the equipment that's out there. And that, I think, is an opportunity. Maybe not quite yet, but it might be an opportunity in the near future.
Yeah. Hey, thank you very much. The space experts gave a really good presentation. I have a question to Mr. Kamath. You mentioned the control system, and I remember so you had the slides that mentioned communication control and defining the communication protocol and developing the operational and dispatching the algorithm. So my background is operation, dispatcher, and telecom automation. So
It's our PKE automation engineer.
Yeah.
Oh, great.
Yeah, and so could you give us the update of what's the current studies for the control system and the software, the protocol, like the standards, the development, or are there any new report, the mature report, or is there any some of the typical way we should go, and that way it can impact the operating, the dispatchers,
Right.
for the grid system?
So things are very much in flux. Things are very much, they're changing. It's very, very nascent. It's a huge opportunity for people who want to get into it. But I will tell you, it's going to take a little while. And the reason is very simple. To have a good control system, you have to have an objective function. You have to have an objective for what you're trying to do. And right now, because frankly speaking, we all talk about energy storage and huge potential and everything else, but nobody knows what it's for. They really don't. And we don't know how to operate it because we don't know what we're trying to do with it. We know roughly what we're trying to do with it, but there are all these different functions that come in and sometimes in conflict with each other. So the control systems guys who are trying to develop these new controls, in many cases, are just throwing up their hands. They say, I don't know how to develop control for this because you want 6 different use cases in the same device, and those use cases may change. They may change in the first half of the year, and there's definitely in the second half of the year. How do we work with that? People are trying to look at that right now. And then there's the separate layers, as Mike brought up. You're not just talking about storage. You're also having demand response. You're also having smart inverters out there. You're having other devices, and so you have to have not only the individual control for each appliance, but also the overall control that orchestrates that, which may belong to the utility, as part of a ADMS or what's increasingly called a DER management system, DERMS. So DERMS is the magic word of the day. Everybody wants a DERMS. Nobody knows what the DERMS is for or what it does, but it's the shiny new object of the moment because we say we're going to control all of these things. So, again, we're still trying to figure that out. That's some of the research that's been going on in my group right now, and we'd be happy to talk to you about it offline in more detail. But standing from a big picture, right now what we have is an unsculpted stone. The stone is very beautiful. It's got great grain, and we know that we can make a beautiful statue out of it, but we don't know what we want to build yet. We have an idea that there's something of great beauty there and value there, but we're still searching for what that exactly might be.
Actually, analogy, beautiful stone, but the first one who does that make a lot of money. Right?
Correct.
Not necessary.
Not necessarily.
Not necessarily.
Cool.
It's usually the second or third one.
The first one nobody go bankrupt.
Yeah. So hopefully, it's a good point because there's a lot of people working on this stuff, but I think that the real strategy for most of these guys is to develop something that works, and then get bought by somebody who can take it to the next level. So it's not necessarily the company that makes it, but we would like to see somebody come out and build something that makes sense.
So I can give you one example also that's relevant here, and that was we did it, like I mentioned, at the Air Force Base frequency response where we use electric vehicles. I have people coming to me all the time, well, you're going to make a fortune with electric vehicles, and we're going to do VDG this and VDG that. Well, when the military put together 6 bases that we're going to do VDG on, they basically estimated they would get about a third of their average lease payment back. They would make a third of their lease payment from VDG services. The only question would be, how much is it going to impact the vehicle battery? Well, after doing that for over a year, we haven't been getting anywhere near a third. We've been getting peanuts when it comes down to it. Now, part of it happens to be with the pricing. So they were looking at pricing 4 or 5 years ago versus pricing today and stuff, and that changes. But I keep reminding people when they look at projects and say we're going to make this big amount of money from VDG, we are supporting that. We're doing projects, we're looking at it all the time. It is an opportunity, like I said, if we're going to have all these vehicles, we've got to find a way to use them. But what I also remind them is you have to have multiple values. You can't bank your future on that. If you're going to bank it on that, it's going to be a losing proposition because you're not going to make enough money back to even cover the cost of interconnection you got to pay. And so what's happening is we just haven't found those lucrative markets yet. I mean, the ones that are working back east are in a niche market. Their rates are different than out here, and the market's different. So we haven't found that some of these transactive energy projects, we're doing a lot of transactive energy projects to work out the logistics and the standards and understand it, but we've yet to have one, with the exception of demand response. Demand response continues to be a good one. It always has been. If you're in the right area, get the right demand response rates, even for residential. But the other ones, that you're trying to improve in the frequency response or the the spinning reserve market, day ahead market. The number this ISO are giving out, the prices they're giving out, is just not high enough to compensate a project if it's not being funded by the government. If it's going to be self-funded, it's difficult to do that. And it's just not a steady enough market. I mean, if you don't know what you're going to get to the next day, you can't predict it a month in advance, a year in advance. You don't even know if you're going to get anything a year in the future. Nobody wants to invest in that kind of thing.
You guys are actually getting to the grant process. Okay, good.
We continue to do analysis because we want to figure out whether this is worth doing or not. So when we go through it, is it worth pursuing all the standards and everything to do that? All I'm saying is, and the ISO will tell you the same thing. If you're going to do a microgrid and you're going to make money, you better plan on more than frequency regulation.
I'm from like a technical point of view. If we have like a typical family have four, so if we are install the flywheel in the basement, so you have all the battery, you have main wheel, you have the solar panel. In particular areas, is anybody to calculate how many efficient have to be input to self-sustain for the energy, and if it's impossible, and how many total energy have to be inside it, what is the scale? All those kind of stuff. Is there any technical data for there? For you calculated like which section you input?
Well, I've seen it from proprietary customers and vendors coming in trying to show me what they have done. They said, if you give me the money, I'll do this. And I say, well, I can't give you money it's going to be proprietary. Plus everything we do is competition. So we can develop a project, and we have done that. We have people come in, and we just recently, a year and a half ago, awarded $30 million from all transactive energy project for doing these types of things. But for example, like energy efficiency, there are incentives, and you can get incentives for those. And the question becomes, you have to do M&V. You have to say before and after. What are you really saving? But there are government incentives beyond the grant that you can do for efficiency and demand responses and those types of things if you're looking for those opportunities, which right now pay more than a tariff would pay.
Is there any target for the government? So this have to be improved certain amount, another have to be certain amount, so in that sense. And what is the ultimately the ideal number of it? Is there any kind of technical data there?
I have no idea.
I think it's online. There's a lot of data out there. But I want to add a comment from the investment side. You heard of 3F investing, right? Anybody heard of it? Normally, a project become a company. It goes through 3F or angel investing. 3F is a family, friends, and fool. Right? So those are the three. But this is really the angel investing right here. This is very, when you have a project, you should go, the first thing you should think about is, especially the energy one, you should go talk to them.
Well, certainly before I leave, I would like to say, and again, either myself or Chin can help anybody here, we put out $150 million a year in competition, and lots of people are getting that money, and we're getting more and more people the first time through. So we really encourage people to do that, and if you don't win an award, we encourage you to come in and get a debrief and learn how to do better next time, because we don't want you to spend a lot of effort and not win. We like to spend, we like to get a variety, we like to support the industry and everybody. So our way of doing that is putting out these solicitations. We have workshops where you help us define what we're going to ask for, and so that we ask for something you want to do. We have had solicitations where nobody responded, period. Nobody responded. That's a waste.
This is all in Sacramento, San Francisco, or South Bay?
No, for all of California. All of ours are all in. And all of our workshops are participated by WebEx, so you don't have to travel to Sacramento to hear them.
Yeah,
you can do. So, there's a link that we can give you that shows you all the stuff that's coming up. You can look at the projects that have passed. And so if you have my information, by all means, I'll be glad to send you to the information. So if you're interested in this opportunity, we want you to look at it. We want you to consider it, and we can help you from there. There's an investment plan for 3-year plan. You can read where we're going to spend our money in 3 years. Yes?
Can I ask if the money you mentioned is from ratepayers?
Yes.
And okay, so that's a question I want to ask you, because you mentioned for venture investors, like 2 out of 10 success will be a good success. But for ratepayers' money, is there a guideline saying you have to be successful at least 50% of the project, or just the money is gone, it's okay?
So we do spend a lot of time on evaluating and reporting the value of what we do. So the benefits of our research is an element that we report to the legislature, report to the PUC, and the public. But the point is, it's different. So he's looking to get his money back. He puts money in, he gets back. We're looking to solve a problem, to advance technology. We're looking to prove something. So, in fact, we say this is a solution that will help lower the cost of electricity. This is a solution that will make it more safe. We've been doing a lot of work lately in natural gas on pipeline safety because of the San Bruno incident and because of what happened in Aliso Canyon. The public doesn't want these things to happen, so we're out there doing. I'm going in a couple of days to go see a site where we have these devices you put on a digger, and it tells you if you're getting close to a pipe so you don't hit the pipe and it blow up and it kill you. So those are technologies we're developing. So we're not interested in that company being profitable, even we'd like it to. We're interested in that technology working, and then if it works, we think they can do it. So our value becomes, what are we doing that provides a value to the ratepayer? When you look at what we do and read our annual report, we report on all that, and you can see what we have done that we think provides safety, value, lower cost, those things to the system. But we don't have a capability of saying, well, we invest in this technology and in 5 years, we're going to get money back.
So CEC probably focused on like a research.
No, it's actually a grant.
Research.
Yeah. It's
Like
a grant.
a DOE
You
grant.
have a report for the grant,
Right.
whatever your results. That's in the answer.
But I know EPIC is repairs money. So another question is what's the investment structure look like for storage market versus the solar market? And when you look at the market policy for storage today, is it similar to 5 years ago to solar, or how do you compare the two?
So I'll try to answer your best I can. So the solar market, over years, we have focused on what was helping California the best. Years ago, it was the price of solar was too high, so we were investing in ways to make the panel cheaper, and then we began investing in ways to make the balance of plant cheaper. We did guidebooks, we did work with things with permitting, and all these things that were heavy cost. So we looked for, and we were successful. Companies were able to build products that were there. In fact, if a company gets a product for us and they sell a product, they do owe us a royalty, or they owe the state a royalty. They pay a royalty for a certain number of years. Not a high royalty, but they pay a royalty to the state. If they invent a product like a new solar panel and it sells a lot of money in a commercial market, then they pay us every year a royalty, which is, we have people do that, but not a whole lot. And the second thing is just becoming in, looking for, for us it's the regulatory issues, learning information to help our decision makers make better decisions in the future. A lot of the research we do is to inform the governor and the legislators and our commissioners so they can make smart decisions as opposed to just making shoot from the hip decisions and finding out. Typically when the government makes a decision to do this or do that very rapidly, it's usually the wrong decision. So what we try and do is give them the different elements and so they can make decisions that's in the best interest of all of California. And so, but we actually do have a section that we have to report on, and what did this money, how does the ratepayer get value from that money, and we have to find that on every single grant that we do.
The question to Haresh, I think Mike is very knowledgeable experience on the California policies, and California is definitely leading the way. And Haresh, I think on your position, you see a lot of the projects in other states or other countries outside of California. So how do you think other maybe hot potential market other than California?
Sure. So let me also say though that as Mike mentioned before, actually, a lot of these other jurisdictions are actually coming to consult California on how this thing. So Mike will have some visibility on what's going on in many of these other jurisdictions. What I can say, and this kind of answers your question as well, on there are a lot of these, there are a lot of people out there who are drawing this analogy for storage and solar, saying that storage was where solar was 5 years ago. I beg to differ, and the reason is twofold. So first of all, solar, the value proposition is very straightforward. It's generating kilowatt hours, it's putting it on the grid, and we have already a very straightforward monetization strategy for solar that's based on those kilowatt hours plus some kind of incentive that's coming around because of the tax credit, the investment tax credit, or production tax credit. In our case, in the U.S., it's an investment tax credit.
So there's a monetization strategy. There is no monetization strategy for storage. So everything that we're doing is on the basis of production targets or a procurement target. Secondly, the ownership model for storage is not clear. So it's very clear for solar that there were developers and there were going to be IPPs and they were the ones that were going to own it, at least in a deregulated market like California. Storage, it's not clear what the ownership model is, because if it's developers, then there has to be a well-developed services market that can actually be monetized and actually get their investment back, as Mike pointed out. But that, just looking at it, for anybody who's done those calculations, it's very hard to actually justify the purchase of a storage system just on the basis of bidding into the services market. On the other hand, you could have the other ownership model, which the PUC seems to have embraced, which is that the storage is either owned or is commissioned by the utilities. And the utilities either pay for it either by owning it and rate basing it, or they rate base some kind of an operation fee that they pay to somebody who owns it. So that's a very different structure.
Follow-up question.
Yeah.
So what do you think about the value proposition given the new time of use default in future years?
Yeah, I mean, we've looked at that, just kind of, again, back of the envelope calculations are not really deep. It's very difficult to make storage pay just on the basis of time of use. Just on the basis of time of use. Now, you could make a case with a stacked benefits case, saying that we're going to get time of use benefits, we're going to get demand charge benefits, we're going to get some kind of subsidy, from the government. For example, the SGIP, the small generation.
So basically, the cost is still too high to get it.
Right now, it is. Now, the question is, in the next 5 years, is that going to change? It's likely to. But maybe not. I wouldn't see it being a weight thing. Time of use rates, there's no way you're going to make a storage system work just by the difference between peak power and off-peak. It's way too small.
So I think Michael Xu is still you already raised your hands long time ago, give you an opportunity.
I guess I've already heard enough to determine that if I were 40 years younger, I would not go into an energy storage market to invent any new thing. Because so far I have not heard anything. For example, solar panel. We know what it is, what it needs to do, right? So I can work out. I might not have enough IQ to do a 0 to 1 to invent yet another solar panel technology. However, I can devote my use and energy to the product cost reduction, which is the more important part, to make it from 1 to 100, from 100 to 1,000 to a million, right? And getting to the business model, right? But I haven't heard anything on energy storage system. For example, like Ember has been a poster child case. Seems like that, okay? But how do you product cost reduce Ember's product?
So let me just say from the value proposition side, I'm not saying that storage doesn't have a value proposition. I'm saying it's more complicated. So for solar, it's one set of value propositions.
Exactly.
Very straightforward, okay? And the thing is that's because it's very straightforward, you could address it with old technology. Everything that's happened in the solar revolution in the last 15 years is with technology that's been around for 40.
Yes.
Right? It's just plain old silicon panels, and we just brought the cost down.
Exactly.
So there's nothing new, no innovation required, really. Frankly, and all the innovation that's happened in the last 10 years, everything that the VCs have put into solar, all of that can just be thrown away. It was.
Indeed.
Because we just basically brought the cost of silicon down. Now, that is not the case for storage. For storage, you can't just take batteries, drag them on the grid, and put them on the grid and make it work. For storage, I actually think that there's more value in the guy who knows how to operate it than the guy who built it. So in the storage case, it's all about the control. It's all about how is that storage being used. And is that a risky value proposition? Absolutely. It is. It's not as simple as solar. It's not as simple as just throwing a bunch of panels out there and making a bunch of money off of it.
Yeah, because we all have a limited amount of use.
Yes.
Right? So if I devoted 20 years of my use to storage, I'm not clear how much.
Well, that's true of anything, right? It's
exactly.
That's true of the software industry.
Devoting 20 years of use to, for example, NVIDIA, I know I could be very wealthy to a certain extent. But I'm not clear devoting 20 years of use to Ember. I'll get the similar.
You mentioned Ember. Let me answer that question. So I have been involved in pushing Ember into China, and in China the monetization is entirely different, right? Because different rates.
Yes.
So one of the things that recently just happened last month is the Southern Grid actually push out a directive, and they actually saying that the kilowatt hours they are putting in money 50 cents, which is 8 cents US dollar, 8 US cents per kilowatt hours. That's a lot, because you think about it, because we have been dealing with customers coming in, not a great customer, but the people who want to do the peak valley upcharge, try to charge at the valley and generate, put energy back into the, and there, our model show the payback is, if it's double, twice charged, because the duck curve. Their payback period typically in the 6 and 7 years. But with that incentive, absolutely every one of them said we want to do it, right? Because it's job back to below 5. And so your payback is below 5. I would say the internal rate is about 12 to 15%. That's a very good payback.
Oh yeah, but I mean,
so there's a now this could be another industry when China is going to be more speed, more advanced than US, because if you look at solar, the manufacturing, because it's very dirty, massive production, it went to China and they were able to reduce the cost dramatically in a very short period of time.
And become
made
profitable.
a lot of the company here bankrupt.
Exactly.
Yes, exactly. They didn't become profitable.
Well,
but that's what happens.
I would think of your comment about storage and cost or your life. I've been in storage about 25 years or more, and I had a discussion with one of my commissioners about 5 years ago. And I said, here's the truth. I said, the first 15 to 20 years I was in storage, I didn't see a price drop of 10% in 15 to 20 years. In the last 5 years, there's been more price drop in storage than I can go back. I mean, there were all kinds of improvements, all kinds of technology, but when you got down to what the price was, it just didn't change. There's actually been a substantial reduction in the last 5 years in what it really costs to buy a system than what it cost you 5 years ago in storage. So I mean, so that if it continues on that path, then it's going to make a difference. If it levels off, it may not.
That path looks similar to solar.
And that's the other thing. I mean, for solar, so let's draw an analogy where the analogy with solar does work. Now, if you talk to people from the solar industry 15 years ago, they would have said like you, I don't see any there, right? There's no value in solar because this is always going to be more expensive than a gas plant. It's always going to be more expensive than a coal plant. What would change?
the change is they moved from U.S. to China. That's the biggest difference. I can't understand.
It wasn't. The biggest difference was that somebody put their finger on the value proposition to make storage solar much more valuable. And when that happened, when there was much more incentive to buy solar, that's when the plants moved to China. Because the China, I mean, there's nobody's dumb. They're not going to build huge plants manufacturing stuff for which there's no market, right? So it's when the market materialized that all of a sudden the cost dropped and all of this happened. So the same thing has happened in batteries. It's starting to happen in storage. It's because of two things. One, it's not just the cost falling. It's also about the benefits rising. And one of the pieces of that, one of those components in that stacked value benefit is a subsidy, or a tax credit or something. Without that tax credit, solar would never have made sense. Now, we're getting to the point where the cost is going down so fast that even if you took away the tax credit, you would still make a profit. And that's the thing in storage is that we will see, I think, in the next few years, a recognition from a variety of entities that storage has some value, some vague value out there. And people are willing to pay for it even though you can't immediately monetize it. And because they're willing to pay for it, the costs come down
and then the monetization strategy become more straightforward.
I'm looking forward to that. But the question is, I mean, for the next 3 years, we know it ain't gonna happen.
I mean, the thing is, no,
I think
hear
it's
you. No, you're right.
4:20 right now. I think let's have one last question, and we will reserve the room until 5. I think after that.
So probably for the panel discussion, let's probably end at 4:30, like another 5 to 6 minutes. Probably one more question. And
I want to answer your question. The M160 is projected at the 475 per kilowatt hours.
Oh wow, that's a good news.
Yeah, so it's coming down.
We might have some hope.
Huh?
We might have some hope in future.
Yeah. Well, I think it's I think the cost down curve is exactly the same with the solar. At the beginning, you gotta have subsidies, and then eventually the subsidy goes away and it become a viable industry.
Yeah, and we have Quencher over there.
Thanks for the demo. I'm just wondering, based on the earlier presentations, there were some discussions about in the developing world when the energy supply was not stable. So I'm wondering what can we learn from the system there, what they have advanced in terms of this kind of storage. What can we, which part of it can be applicable or which part of it is limited by our own current system?
So,
have you heard clearly?
Yeah, I heard it anyway. So let me make sure I understood the question properly. You're asking what lessons we can learn from developing countries and what they're doing with in their grids that that may be applicable to our grids here. So there's a considerable amount of information that we can learn from each side, right? I mean, both sides have their advantages or their approaches that we can learn from. What we've seen in a lot of developing countries is that the grids are relatively weak, and they're weak to start out with. So, throwing a lot of renewables on those grids is not going to help the situation, generally speaking. So, but we've also seen that there's a lot of customer intervention in those places. So, a lot of customers have their own voltage regulator. They have their own backup battery system. Which is really interesting. You don't really usually see those things in this area. And the question is whether we can apply those technologies, in the U.S. or in other developed countries. The bottom line is really what is the lowest cost way of achieving what the customer wants in the long run. People don't really want a battery, right? The battery is just a means to an end. What they want is low cost, reliable, safe, cost-effective power, right? And so, a lot of folks in this industry will come in and say, well, I want distributed generation, or I want it all to be renewable. Well, most customers don't say that. So it's our job to define what we really want. And if that's safe, clean, reliable, cost-effective, then we can define it. And I think that that's a lot easier to figure out in many of the developing countries because they don't have a lot of sunk cost in infrastructure that we do here. And maybe we can use those technologies, at least maybe even for early deployment, for testing in the developing world, or in places where the capital investment is just now happening. And maybe even some of the approaches that we take in those areas will be different. For example, here in the U.S., we typically tend to amortize our grid investment over 40 years. And 40 years is a very long time. That means that we have to have equipment that actually lasts that long. But could you create a monetization strategy or rather a payment strategy for that infrastructure that doesn't take quite so long? Can we still make it cost effective if we amortize it over 20 years or 10 years? And that's something that can be tried out in many developing nations, I think, much more easily than we can try here.
Yeah, I was going to say that the interesting thing for me in Puerto Rico and Florida is that you asked the question, could we design a system better, cheaper now with what we know? And I believe we could, but the truth is, in Puerto Rico and Florida, they're going to put the old system back up first. So they're putting up the poles. I mean, they're replacing with new poles. They're replacing with new wire. There may be a better transformer, but the truth is, they don't want to wait for some kind of monumental change. So there is a real opportunity to solve that problem better, but it's just not going to happen because we're not ready for that. But I do think that there's a time where it's a starting, emerging company, the country is growing its first real grid, for some reason, but you could do it a lot smarter, a lot better, and a lot cheaper with renewables and with what we use here. It's just the fact that right now, everybody wants to put that classical system in first and then add everything else to it.
So I think this is really the last one. Okay.
Microgrid. So you mentioned the several microgrid. What's the situation right now in California, like based on the experience, the microgrid, whether or not they have the commercially ready?
So I mean, the situation is we're learning a lot, and we're kind of leading the effort right now. We have 7 that we're funding. We have another substation for $45 million. We'll fund another 8 to 10, and those are specifically developed to do the business case for a repeatable microgrid. So we put the substation. We said, give us a microgrid that you can build and it has a future market. So, we're trying to do that. We have a roadmap we're publishing that I'm working with the other 2 agencies, and we've had 4 or 5 workshops, and we're getting ready to publish a final document. The title of it is Commercializing Microgrids in California. So the focus is to make, because there's no policy for microgrids. We don't have any policies that says you must have 50% microgrids. You must have a microgrid in every city, like or a pot, chicken in every pot. It doesn't work that way. The point is we're going microgrid because we think it's the smart, cost-effective way to meet those policies, to get the distributed generation, to get the reliability, to get the lower cost. So we are working hard. Now, we don't have that answer now. We have different ones. But we're actually evolving to the point of trying to figure out. My experience has been, having done this for the last couple of years, I believe microgrids will be like cars in the sense that when I tell somebody, I'm going to go buy a car, well, that's not an answer. What are you going to buy? You're going to buy an economy car, a family car, a station wagon, a pickup truck, a race car, a van. So I think microgrids are going to come up into inexpensive microgrids, medium, and expensive microgrids. We had a discussion in one of our workshops, microgrid controller. You can get a controller for $10,000. You can get one for $1 million. What do you want to pay for it? What do you want it to do? And so I think what's going to happen is I don't believe the grid will be a grid of microgrids. That's one of the questions we have. But I think the grid will evolve to where there are locations where microgrids make all the sense in the world, and that's where they'll show up. We just don't have that defined yet.
Okay, let's give up.
Yeah.
Thank you so much.
Wonderful.
The room reserved to 5 if anybody still wants to.